When we train an AI, the standard way to do it is to reward it for finding the single best answer. It makes sense, right? But our team started to ask a really critical question. What if that very approach, the thing we've always done, is actually holding our AI back? So we started exploring a completely different way to train AI, a method that values creativity and exploration just as much as it values getting the right answer.
And really, to get to the heart of our work, you just need to think about this one question. What if an AI, when you give it a really tough math problem, could come up with not just one correct solution, but multiple, totally distinct, and equally valid ways to solve it? That single question was pretty much the starting point for this entire project.
So here's the crucial difference in approach. Standard AI training is kind of like following the main highway to get your destination. It's fast, it's efficient, sure, but it's always the same exact route. Our method, which we call Poly-EPO, is totally different. It's about building a map of all the roads, including the little scenic backroads you never even knew existed.
Now, to understand why exploring all those roads is so important, we first have to talk about a fundamental issue we kept seeing with current AI training. We started calling it the one-trick problem. I want you to imagine a manager who's training a team of problem solvers. Every single time someone on the team presents a safe, conventional solution that works, they get a big bonus. But any ideas that are a bit different, a little outside the box, even if they also work, they just get ignored. So what do you think happens to that team? Well, pretty soon, everyone just starts copying that one safe strategy over and over again. They completely stop being creative. They become a one-trick pony. And this is exactly what we see happening with AI during standard training.
And look, this isn't just a fun analogy. We have the data to prove it. Now, what's really fascinating on this slide is that orange line. That represents standard AI training. On the side there, the y-axis, that's the number of different correct strategies the AI finds. You can see it starts out with a little bit of diversity, but then, very quickly, it just collapses down to one popular strategy. It totally stops exploring.
So, the big question became, how do we fix this? We realized we had to completely rethink the role of that manager. We needed a whole new approach for training a team that was more creative and way more versatile.
The whole foundation of our solution is this concept called set reinforcement learning. It's a bit of a mouthful, but the idea is simple. Instead of judging each answer one by one, we judge a whole set of answers at the same time. We reward the entire group for being both correct and diverse.
So let's go back to our analogy. The new manager, our new training method, doesn't give out bonuses to individuals. Nope. Instead, they look at the entire portfolio of solutions from the whole team, and they give a massive team-wide bonus if that portfolio has a wide variety of successful ideas. Suddenly, everyone on the team has a reason to think differently.
Okay, so that's the big idea. And that led us to develop our specific framework, which we call Poly-EPO. It stands for Polychromic Exploratory Policy Optimization. And here's a quick breakdown of how it actually works under the hood.
The real secret sauce is what we call the polychromic score. For any group of solutions the AI comes up with, we calculate a score that's basically just two things multiplied together: how accurate the solutions are on average and how many different strategies they represent. To get a high score, you absolutely have to do well on both.
So here's the process in a nutshell. First, the AI generates just a whole bunch of potential solutions. Second, we group those solutions into lots of little teams. Third, we use another AI, which we call an LM judge, to score each of those teams using that polychromic score. And then finally, and this is the really key part, we give credit back to the individual solutions that help make their teams more creative and successful in the first place. Okay, so that's all the theory. But the billion-dollar question is, does it actually work in practice? We ran a whole series of experiments on some very difficult mathematical reasoning problems, and honestly, the results were pretty exciting.
This chart here shows something called the Pascal rate. It's basically the chance of solving a problem if you get k number of attempts. And this just brilliantly illustrates the power of our approach. See that blue line? That's Poly-EPO. As you give it more and more tries, its success rate just climbs like a rocket, way faster than the standard methods. This proves it's not just repeating itself, it's genuinely trying different, successful strategies.
We can even visualize the AI's thought process. I mean, look at this. On the left, you've got the Poly-EPO reasoning tree, and immediately just branches out, exploring tons of different directions all at once.
Now compare that to the standard method on the right, which just follows this one single narrow path. The difference in exploration is it's stark.
And this diversity pays off in another really practical way, voting. A common technique with AI is to generate many answers and then just let the majority rule. As you can see in this chart, Poly-EPO's accuracy, that top blue line, climbs way higher as you add more voters. And that's because its answers aren't just copies of each other. They bring genuinely different perspectives to the table, and that leads to a much more robust and reliable final decision.
So let's just pull back for a second and look at the bigger picture here. Why is training an AI to think this way so important? Well, it really comes down to a fundamental shift in how we approach machine learning itself.
We call this guiding principle optimistic exploration. It's this core idea that we should be encouraging novel strategies and new ways of thinking, even if they don't immediately lead to a perfect answer.
This is a key line from our paper, and it really gets to the absolute heart of the matter. Our algorithm can actually give a positive learning signal to an attempt that was creative, that tried a brand new strategy, even if that attempt failed.
Let's bring it back to our team one last time. This means that a team member who suggests a wild, out-of-the-box idea gets credit for it. Even if their specific solution was a little flawed, their idea expanded the team's strategic playbook. It made the whole group more innovative. We are rewarding the exploration itself. And all of this, it leads us to one final, really big question. We've shown that it's possible to train an AI that doesn't just find the known answer, but one that actively explores the entire universe of all possible answers. So, what happens next? What new scientific discoveries, in fields from drug discovery to material science? Or what incredible creative breakthroughs become possible when our AI partners are trained to be every bit as strategically diverse and creative as we are?